Imagine being able to discover the chemical composition of a star millions of light years away without ever leaving Earth. It sounds like magic, but it's pure science. And the secret lies in something as tiny as electrons, yet as vast as the universe itself: spectral lines. Today, we're going to explore how the quantization of electron orbits reveals the secrets of stars and helps us decipher the cosmos. Picture yourself as an ancient astronomer, gazing at the night sky, wondering what those twinkling lights are made of. For thousands of years, this remained one of humanity's greatest mysteries. But everything changed when scientists began understanding the fascinating world of atoms and their electrons. The story becomes even more intriguing when we look at how these discoveries unfolded. Back in 1913, a brilliant Danish physicist named Niels Bohr proposed something revolutionary. He suggested that electrons don't just orbit atomic nuclei randomly. They follow specific, quantized paths, like cosmic dancers performing a carefully choreographed routine. Here's where it gets truly fascinating. When these electrons jump between their designated orbits, they either absorb or emit light of very specific colors. It's like each element in the universe has its own unique light signature, its own cosmic fingerprint. Just as each person has a distinct voice, each element has its distinct spectral pattern. We're about to dive deep into Bohr's atomic model, understand how electrons jump between orbits, and discover how this creates the spectral lines that astronomers use to unravel the composition of stars. Get ready for a journey that connects the microscopic to the astronomical, from the atom to the galaxies. Think about it. The same principles that govern the tiniest particles in an atom allow us to understand the composition of massive stars trillions of miles away. It's one of science's most beautiful connections, showing us how the universe follows the same rules whether we're looking at something through a microscope or a telescope. This remarkable tool of spectroscopy has led to some of astronomy's most groundbreaking discoveries. Did you know that helium was actually discovered in the sun before it was found on Earth? Scientists noticed unknown spectral lines in solar observations and realized they were looking at an entirely new element. We're about to embark on an incredible journey through the quantum realm and into the cosmos. Together, we'll explore how these microscopic quantum leaps help us understand the biggest objects in our universe. This is the story of how humanity learned to read the light from the stars, decoding messages that have traveled across space for millions of years to reach us. The universe is about to share its secrets with us, one spectral line at a time. Get ready for a mind-bending adventure that connects the infinitely small with the infinitely large. Before we continue, don't forget to like the video and subscribe to the Exploring the Universe channel so you don't miss any content about the fascinating world of astronomy. Let's dive into one of the most fascinating models in atomic physics, the Bohr model. Picture an atom as a tiny solar system, but instead of planets orbiting the sun, we have electrons dancing around a nucleus. This elegant model was proposed by Niels Bohr in 1913. And it revolutionized our understanding of the atomic world. In this microscopic dance, electrons don't just orbit anywhere they please. They follow specific predetermined paths, like invisible tracks in space. These tracks, or energy levels, are what we call quantized orbits. Think of them as cosmic highways, where electrons must travel, with no possibility of cruising in between. But here's where it gets really interesting. Why don't the electrons simply crash into the nucleus? After all, opposite charges attract, right? The classical laws of physics would suggest these negatively charged electrons should spiral down and collide with the positively charged nucleus. But they don't, and this is where the magic of quantization comes in. Quantization acts like an invisible force field, keeping electrons in their designated orbits. It's nature's way of saying you can be here or there but nowhere in between. This quantum rule prevents electrons from falling into the nucleus, maintaining the stability of atoms and, by extension, everything in our universe. Here's something that will blow your mind. If we could expand an atom to the size of a football stadium, the nucleus at its center would be no bigger than a tiny pea. The rest would be mostly empty space with electrons zipping around in their quantum highways. Imagine that. The solid matter we see and touch around us is mostly empty space. This quantum dance of electrons isn't just a theoretical curiosity. When electrons jump from one allowed orbit to another, they either absorb or emit specific amounts of energy in the form of light. This is exactly what creates the spectral lines we see when studying starlight, but we'll get to that fascinating connection in just a moment. The Bohr model might seem simple, but it solved one of the biggest mysteries in physics at the time. Before Bohr, scientists couldn't explain why atoms only emitted and absorbed specific colors of light. His quantum model provided the first clear explanation of these spectral lines, opening a new chapter in our understanding of the universe. And here's a delightful historical tidbit. When Bohr first presented his model, many of his colleagues thought it was too radical. The idea that electrons could only exist in specific orbits seemed to violate classical physics, but sometimes the most revolutionary ideas in science are the ones that challenge our basic assumptions about how the world works. The beauty of the Bohr model lies not just in its ability to explain atomic behavior, but in how it bridges the gap between the microscopic world of atoms and the macroscopic world of stars. It's a perfect example of how understanding the tiniest building blocks of matter can help us unravel the mysteries of the entire cosmos. Light is truly extraordinary. It's not just the brightness that illuminates our world, but a cosmic messenger carrying secrets from the farthest reaches of space. Every beam of starlight that reaches Earth is like a letter from the cosmos, packed with information about the star that sent it. Think about this. When you look up at the night sky, you're not just seeing stars as they are now, you're looking into the past. The light from our closest stellar neighbor, Proxima Centauri, takes 4 years to reach us, and that's just our cosmic backyard. The light from the Andromeda galaxy has been traveling through space for an astounding 2.5 million years before reaching your eyes. When that light first began its journey, our human ancestors were just learning to use stone tools in Africa. The famous physicist Niels Bohr once said, "Physics is not about how the world is, but about what we can say about it." This profound statement perfectly captures how we use light to understand the universe. We might never be able to visit distant stars, but their light tells us incredible stories about their composition, temperature, movement, and even their age. Here's something fascinating. Each element in the universe leaves its unique fingerprint in starlight. When you split starlight through a prism, like in Pink Floyd's famous Dark Side of the Moon album cover, you're actually seeing much more than a pretty rainbow. Those colors contain dark and bright lines that astronomers can read like a cosmic barcode, revealing exactly which elements are present in that star. Remember those chemistry classes where you heated different elements and they produced different colored flames? Stars do exactly the same thing, but on an unimaginably larger scale. The light from stars is produced by elements being heated to millions of degrees, each one adding its own signature to the stellar light show. The story of how we learn to read starlight is filled with brilliant insights and lucky accidents. In 1814, Joseph von Fraunhofer was actually trying to improve telescope lenses when he discovered dark lines in the sun's spectrum. He had no idea he'd just opened a window that would allow us to understand the chemical makeup of stars billions of light years away. And here's a mind-bending thought. The light reaching us from distant stars has traveled through space virtually unchanged since it left its source. It's like having a time capsule delivered directly to Earth, carrying information from centuries, millennia, or even millions of years ago. When you look at the star Betelgeuse, you're seeing light that left that star around the time the first European settlers were arriving in America. This cosmic light show isn't just beautiful, it's our most powerful tool for understanding the universe. Every photon that reaches our telescopes carries vital information about its journey through space and time. It's as if the universe itself is sending us messages written in the language of light, just waiting for us to decode them. The next time you look up at the night sky, remember that you're not just seeing points of light. You're witnessing ancient messages finally reaching Earth after epic journeys across the cosmos. Each twinkling star is sharing its story with us, one beam of light at a time. Now let's explore one of the most fascinating dances in the universe, the quantum leap of electrons. Imagine electrons as tiny acrobats, jumping between different energy levels in an atom. These aren't just random jumps, though. They're precisely choreographed moves that follow the strict rules of quantum mechanics. When an electron gets excited, maybe by absorbing heat or light, it jumps to a higher energy orbit, like a performer leaping to a higher platform. But here's the amazing part. Electrons can't stay excited forever. Eventually, they have to come back down to their original level, and when they do, they release their extra energy in the form of light particles called photons. It's nature's own light show. Think of it like an elevator in a very strange building. The elevator can only stop at certain floors, no stopping between levels. When going up, the elevator needs exactly enough energy to reach the next floor. When coming down, it releases that same amount of energy. In the atomic world, this released energy takes the form of light with very specific colors. Here's where it gets really interesting. Every element in the periodic table has its own unique set of possible electron jumps. It's like each element has its own special choreography. Hydrogen's electrons perform different jumps than helium's electrons, which jump differently than iron's electrons, and so on. This creates a unique pattern of spectral lines for each element, a cosmic fingerprint that we can detect even across vast distances in space. Let me share a fascinating historical tidbit. In 1868, astronomers noticed some strange spectral lines in sunlight that didn't match any known element on Earth. They named this mysterious element helium, after Helios, the Greek sun god. It wasn't until 27 years later that helium was finally discovered on Earth. This shows how studying electron transitions can lead to groundbreaking discoveries. The patterns created by these electron jumps are incredibly precise. When you heat up sodium in a flame, it always glows with the same yellow color. This happens because sodium's electrons always make the same jumps, emitting the same wavelengths of light. It's like each element has its own signature tune in the cosmic symphony. This precision is what makes spectroscopy such a powerful tool in astronomy. Whether we're looking at a street lamp in our neighborhood or a star billions of light years away, sodium will always create the same pattern of spectral lines. It's like having a universal barcode reader that works across the entire cosmos. Speaking of elements in stars, there's an incredible variety out there. While most stars are primarily made of hydrogen and helium, they can contain traces of everything from carbon and nitrogen to more exotic elements like gold and platinum. Each of these elements adds its own unique lines to the star's spectrum, creating a complex but readable pattern that tells us exactly what that star is made of. You might be wondering which elements are the most interesting to study in stars. While hydrogen is the most abundant and tells us a lot about stellar evolution, some astronomers get excited about finding heavy elements like gold or platinum in stars, as these tell us about explosive stellar events like supernovas. Others focus on elements like carbon, nitrogen, and oxygen because they're essential for life as we know it. It's amazing to think that these microscopic electron jumps, happening countless times every second in atoms everywhere, give us the power to understand the composition of objects millions of light years away. Every time you see a star twinkling in the night sky, Remember that its light carries the signature of countless electrons, all dancing their precise quantum dance. Let's explore one of astronomy's most powerful tools, spectroscopy. Imagine having a device that can split starlight into its component colors, just like a prism creating a rainbow. That's exactly what a spectrograph does, but with incredible precision that reveals the chemical fingerprints hidden in starlight. When astronomers point their spectrographs at stars, they see more than just pretty colors. They observe a pattern of dark and bright lines, like a cosmic barcode, that tells them exactly which elements are present in that star. It's like being able to read a star's ingredient list from millions of light years away. Here's a remarkable story that shows the power of spectroscopy. Back in 1868, astronomers were studying the sun's spectrum when they noticed some mysterious dark lines that didn't match any known element on Earth. They named this unknown element helium, after the Greek sun god Helios. It wasn't until 1895 that helium was finally discovered on Earth in uranium ore. Think about that. We found an element in the sun before we found it on our own planet. But perhaps one of the most inspiring stories in spectroscopy is that of Cecilia Payne-Gaposchkin. In 1925, this brilliant astronomer made a discovery that would completely change our understanding of the universe. Using spectroscopy, she figured out that stars are made primarily of hydrogen and helium, a finding that contradicted the scientific consensus of her time. The scientific establishment initially rejected her conclusion, believing that stars had roughly the same composition as Earth. Can you imagine the courage it took for a young female astronomer in the 1920s to challenge the leading minds of her field? But she was right, and her work revolutionized our understanding of stellar composition and evolution. The spectrograph itself is like a cosmic detective tool. When starlight enters the instrument, it passes through a narrow slit and then hits a prism or diffraction grating that spreads the light out into its spectrum. Modern spectrographs are so sensitive they can detect elements present in incredibly tiny amounts. It's like being able to taste a single drop of lemon juice in an Olympic-sized swimming pool. Here's something fascinating. Spectroscopy doesn't just tell us what stars are made of. It also reveals their temperature, speed, rotation, magnetic fields, and even whether they're moving toward or away from us. When we see spectral lines shifted toward the red end of the spectrum, we know the star is moving away from us. If they're shifted toward the blue end, the star is coming closer. This discovery led to one of astronomy's biggest revelations: the expansion of the universe. Each chemical element creates its own unique pattern of spectral lines, like a signature written in light. Hydrogen, the most abundant element in the universe, produces a distinctive pattern called the Balmer series. Sodium creates two very strong lines in the yellow part of the spectrum, the same lines that give sodium street lamps their characteristic orange glow. Modern astronomers use incredibly sophisticated spectrographs attached to powerful telescopes to study stars, galaxies, and even the atmospheres of distant planets. These instruments are so precise they can detect the subtle wobble of stars caused by orbiting planets, leading to the discovery of thousands of worlds beyond our solar system. And before we move on to our next topic, I'd love to hear from you. Which element would you most like to detect in a star? Maybe iron, which forges the cores of massive stars, or perhaps something more exotic like neon, which can create some of the universe's most colorful nebulae. Share your thoughts in the comments below. If you're enjoying this cosmic journey through spectroscopy, don't forget to hit that like button and subscribe to Exploring the Universe. We've got many more fascinating stories about the cosmos coming your way. Let's explore how spectral lines have become the Swiss Army knife of astronomy. These amazing tools tell us far more than just what stars are made of. They're like cosmic thermometers, speedometers, and compasses all rolled into one. When astronomers look at spectral lines, they're reading multiple stories simultaneously. The width of these lines tells us about a star's temperature. The broader the lines, the hotter the star. Think of it like watching a pot of water. Just as water molecules move faster as they heat up, atoms in hotter stars move more rapidly, creating broader spectral lines. But that's just the beginning. The brightness and darkness of different spectral lines reveal the star's chemical makeup with incredible precision. For instance, if you see strong hydrogen lines but weak calcium lines, you're likely looking at a young, massive star. It's like being able to read a star's recipe from across the galaxy. Here's where it gets really exciting. Spectral lines also tell us how stars are moving. When a star moves away from Earth, its spectral lines shift toward the red end of the spectrum, what we call redshift. If it's moving toward us, they shift toward the blue end. That's blue shift. It's similar to how a train's whistle changes pitch as it passes by, but with light instead of sound. This redshift phenomenon led to one of the most groundbreaking discoveries in the history of science. In the 1920s, Edwin Hubble noticed that the farther away a galaxy was, the more its spectral lines were shifted toward the red. This seemingly simple observation led to an earth-shattering conclusion. The universe is expanding. But wait, there's more. In the 1990s, astronomers studying distant supernovas made an even more astonishing discovery. Not only is the universe expanding, but this expansion is accelerating. It's as if some mysterious force, which we now call dark energy, is pushing everything apart faster and faster. Think about what this means. Every second, the cosmic web of galaxies is stretching further apart. It's like raisins in a rising loaf of bread, except this loaf will keep expanding forever. This discovery was so revolutionary, it earned the scientists involved the Nobel Prize in Physics in 2011. Spectral lines even help us study objects we can't see directly. By measuring how stars wobble due to the gravitational pull of orbiting planets, astronomers can detect these distant worlds and even estimate their mass and size. It's like knowing there's a dog pulling on its leash just by watching how the owner moves. Here's a mind-bending fact. Using spectral lines, we can also measure a star's rotation speed and magnetic field strength. When a star spins rapidly, one side moves toward us while the other moves away, creating a characteristic broadening of spectral lines. It's like taking a star's pulse from thousands of light years away. The applications of spectral analysis keep growing. Today, astronomers use it to study everything from the atmospheres of distant exoplanets to the mysterious dark matter that pervades our universe. We can even use spectral lines to detect the chemical signatures of potential life on other worlds. This brings us to a fascinating question about our cosmic future. If the universe keeps expanding faster and faster, what will the night sky look like billions of years from now? Will future astronomers see fewer galaxies? Will the cosmos eventually become a vast, empty space with islands of galaxies too far apart to see each other? What do you think about this cosmic expansion? Will the universe keep accelerating forever, or might there be some yet undiscovered force that could reverse this expansion? Share your thoughts in the comments below. Are you as fascinated by these cosmic mysteries as I am? Now let's dive into something that will truly blow your mind. Did you know that thanks to the quantization of electron orbits, those tiny quantum leaps we've been talking about, we're not just studying stars anymore? We're actually using this knowledge to detect habitable planets in other solar systems. Yes, you heard that right. Those same spectral lines that reveal the chemical makeup of stars are now helping us search for worlds that might support life. Here's how it works. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere. And guess what? The atmosphere leaves its own spectral fingerprint in that light. By analyzing these fingerprints, astronomers can detect whether a planet has water vapor, oxygen, methane, or even signs of potential biological activity. It's like reading a cosmic message in a bottle. But instead of a note, it's a planet's atmosphere telling us whether it might be habitable. But here's where it gets even more profound. This connection between electron orbits and spectral lines isn't just about science. It's about one of the biggest questions humanity has ever asked. Are we alone in the universe? Every time we study the light from a distant star or planet, we're essentially searching for answers to this age-old question. Think about this for a moment. The same principles that explain how electrons jump between orbits in an atom are now helping us explore the possibility of life on other worlds. It's a beautiful reminder of how interconnected everything in the universe truly is, from the tiniest particles in an atom to the vast expanse of space. Here's a fascinating historical tidbit. Back in the 1990s, when astronomers first started discovering exoplanets, they were mostly finding gas giants like Jupiter. But as our tools and techniques improved, we began finding smaller, rocky planets, some of which sit in the so-called Goldilocks zone, where conditions might be just right for liquid water and life. And here's something truly inspiring. In 2016, astronomers discovered Proxima b, a rocky planet orbiting Proxima Centauri, the closest star to our solar system. It's just 4.2 light-years away, practically our cosmic neighbor. While we don't yet know if it's habitable, the discovery has fueled our imagination and our determination to keep searching. So the next time you look up at the night sky, remember this: every star you see could be home to planets. And some of those planets might have atmospheres with the right conditions for life. And it's all thanks to the quantum dance of electrons and the spectral lines they create. This isn't just science, it's a journey of discovery, a quest to understand our place in the cosmos. And who knows, one day we might find that we're not alone after all. What do you think? Could there be life out there waiting to be discovered? Let me know your thoughts in the comments. As we wrap up our cosmic journey today, let's take a moment to marvel at what we've discovered. We've seen how the quantum dance of electrons creates the spectral lines that illuminate our understanding of the universe. These microscopic movements, following precise quantum rules, give us a window into the composition of stars billions of light-years away. And through spectroscopy, we've gained a powerful tool that lets us explore the cosmos from right here on Earth. Think about this. Every time you look up at the night sky, you're seeing countless stories written in light. Each twinkling star is sending us a message encoded in its spectrum, telling us about its chemical makeup, its temperature, its motion through space, and even its life story, from birth in a stellar nursery to its eventual fate. Our ability to read these cosmic messages represents one of humanity's greatest achievements. Just 200 years ago, people could only wonder what stars were made of. Today, we can analyze the chemical composition of galaxies so distant that their light has been traveling toward us since before dinosaurs walked the Earth. This is more than just scientific progress. It's a testament to human curiosity and ingenuity. You know what amazes me most? The same physical laws that govern an atom in your fingertip also apply to the largest stars in the most distant galaxies. The universe speaks one language, the language of physics, and we've learned to understand it. Every discovery we make, from quantum mechanics to spectral analysis, adds another word to our cosmic vocabulary. We've taken an incredible journey together today, from the quantum realm of electron orbits to the vast expanses of space. But our cosmic adventure doesn't end here. The universe has so many more secrets to share with us. Next time we meet, we'll dive into one of the most mysterious phenomena in the cosmos: black holes. We'll explore how these cosmic giants bend not just light, but the very fabric of space and time itself. The universe is our greatest teacher, and every night it puts on a spectacular show just for us. So the next time you look up at the stars, remember, you're not just seeing points of light, you're witnessing billions of years of cosmic history, written in a language that humanity has finally learned to read. Thank you for joining me on this journey through the quantum realm and into the stars. If you've enjoyed unraveling these cosmic mysteries, make sure to join our growing community of space enthusiasts by subscribing to Exploring the Universe. Hit that notification bell to stay updated on all our upcoming cosmic adventures. Share this video with your friends who love gazing at the night sky. Let's spread the wonder of science together.